One of the best things about complex numbers is how they provide a really elegant way to describe and manipulate rotations in 2 dimensions. The epitome of this ability is Euler's formula, which provides a way to rotate a vector by any angle. All you have to do is multiply your vector, expressed as a complex number, by e to the power of theta times I, and the result is the vector rotated theta radians counterclockwise. The upshot of describing 2D rotation this way is we can import the familiar algebra rules for manipulating exponentials to help us analyze rotations. So Euler's formula provides a way to study rotations using the algebra of exponentials. Unfortunately, this magic is limited to 2D by default, since complex numbers can't really describe anything in 3D or higher dimensions. But by going beyond complex numbers and entering the strange and beautiful world of matrices and linear algebra, we can find an analog of Euler's formula that works in any dimension, a way to describe any rotation in any dimension using exponentials. We laid the groundwork for this in a previous video, which I very much recommend you watch if you want the full story at a more reasonable pace. Link in the description. But to summarize, we developed the concept of what I called a tilt product, which is a certain way of combining 2 perpendicular unit vectors, u and v, to produce a matrix which, when multiplied by a vector, has the effect of projecting that vector onto the UV plane, and then rotating the vector 90 degrees in the direction from u toward v. Plugging in such a matrix scaled by an angle theta into the matrix exponential, a certain way of raising e to the power of a matrix, produces a rotation matrix that has the effect of rotating vectors theta radians in the direction from u toward v. In this video, we'll develop a formula analogous to the classic Euler's formula that provides an easy way to calculate e to the theta g for any tilt product matrix G, as well as show how to use these matrix exponentials to solve a concrete problem. This video will be a bit heavier on the algebra than usual, but that's honestly kind of the essence of the topic here, as the end result is a handy set of algebraic tools you can use to describe and manipulate rotations in 3D or higher dimensions. So if you can stomach some algebra, I think the takeaway here will be powerful and well worth it. Okay, so buckle up and let's get started. The goal is to find a closed-form formula for the matrix expression e to the theta times u tilt v, where u and v represent perpendicular unit-length vectors in any dimensional space. First, recall that the definition of raising e to the power of a matrix is to plug the matrix into this infinite series, which is inspired from the Taylor series expansion of the regular real-valued e to the x function. This looks complicated, but things are about to simplify quite a lot. The key is to observe that powers of a tilt product matrix fall into a certain pattern, and eventually repeat. Remember, the tilt product, u tilt v, is a matrix that has the effect of projecting a vector onto the UV plane and rotating it 90 degrees. If we apply this transformation twice in a row, which is what squaring it means, the vector will be projected again before undergoing a second 90-degree rotation. But since the vector was projected onto the UV plane once already, the second projection does nothing. So the tilt product squared acts on a vector by projecting it onto the UV plane and then rotating it 180 degrees. But rotating a vector 180 degrees is the same as negating that vector, multiplying it by -1. So the tilt product squared is really the same thing as the negative projection matrix onto the UV plane. For vectors that already started out in the UV plane, projection does nothing, so the tilt product squared will simply negate that vector. And since tilt products always project vectors onto the UV plane to begin with, it means every time we multiply a power of a tilt product by the tilt product squared, we simply negate the original tilt product power. So u tilt v cubed is just negative u tilt v, and u tilt v to the 4th power is just u tilt v squared twice, so it equals negative u tilt v squared. And u tilt v to the 5th power is just u tilt v squared twice times a single u tilt v, which results in a double negative, so it's just u tilt v. And from here, the cycle just repeats. So any power of a tilt product can be written as either positive or negative u tilde v, or its square. With that in mind, if we take our power series expansion for the matrix exponential and group terms by powers that differ by a multiple of 2, we can simplify the higher powers of u tilde v by repeatedly subtracting 2 off the exponent, flipping the sign each time we do. And in the end, we wind up with 2 separate infinite series. One consisting of alternating fractions of odd powers of theta, all multiplied by a single tilt product, and another series consisting of fractions of even powers of theta, all multiplied by the tilt product squared. Those of you who have had some calculus might recognize the 2 series we're left with. They're basically the Taylor expansions of the sine and cosine functions. Specifically, our alternating series with the odd powers of theta is precisely the infinite series representation of sine of theta. And the second alternating series is actually the series expansion for 1 minus cosine of theta. So the end result is a short formula for e to the theta u tilde v. The identity matrix I plus sine of theta times u tilde v plus the quantity 1 minus cosine of theta times u tilde v squared. And that's it. That's our generalized Euler's formula that works in 3D or even higher dimensions. What do you think? Does it remind you of the classic Euler's formula for complex numbers? Cosine of theta plus I sine of theta? I'll admit it's a little more complicated, but I think you can see the resemblance. In fact, why don't we derive the original Euler's formula from this generalized one? It's not too hard. First, we have to express the imaginary number I in the language of vector tilt products. The role of I in the complex plane is to rotate vectors 90 degrees counterclockwise. So in vector matrix land, this is accomplished by the 2D tilt product I hat tilt j hat. Remember, we can ignore the projection aspect of tilt products here because we're in a 2D setting and all the action takes place within the xy plane. Plugging theta times I hat tilt j hat into our general Euler's formula, we get the following equation. But now remember how a tilt product squared is the same as a negative projection matrix? But since we're in 2 dimensions here, no projection is needed. So the negative projection matrix given by I hat tilt j hat squared is just the same as the negative identity matrix, the matrix that simply negates any vector it multiplies. Distributing this negative identity matrix through, we'll find that one copy of it cancels with the leftmost identity matrix we started with, leaving behind only the expression sine of theta I hat tilt j hat plus cosine of theta times the identity matrix. And if we swap the order of the terms here, and remember that I hat tilt j hat serves the same purpose as the imaginary number I, we've actually reproduced the classic 2D Euler's formula. Multiplying a vector by this expression produces the same result as multiplying a complex number by cosine of theta plus I sine of theta. So our generalized Euler's formula seems legit. It even reduces to the classic Euler's formula in the 2D case. But I can hear some of you shouting at your screens about how similar it looks to another rotation formula, the Rodriguez rotation formula. If you haven't heard of it, the Rodriguez rotation formula is a method for efficiently rotating a vector in 3D space. And one of the forms you'll see it written in matches almost exactly with our generalized Euler's formula. So in a very real sense, the Rodriguez rotation formula is a generalization of Euler's formula. However, the Rodriguez formula is usually expressed in terms of cross products, and so technically only describes 3D rotations. But by swapping out cross products for tilt products, we find it actually generalizes far beyond 3D. Now I don't know about you, but I'm itching to try out this new mathematical toy on something. Let's see what it can do. One of the reasons I became so interested in finding a higher dimensional analog of Euler's formula was to see if it were possible to re-express spherical coordinates as an algebraic expression, similar to how it can be done for polar coordinates. Because in 2 dimensions, Euler's formula provides a very natural way to algebraically express and manipulate polar coordinates. If you have a radius r and an angle theta representing the polar coordinates of a point in the plane, then packaging them together as the expression re to the theta I encodes those polar coordinates algebraically, and the expression itself, when evaluated, results in the unique complex number those polar coordinates correspond to. The real part of this expression is the x-coordinate, and the imaginary part is the y-coordinate, and the absolute value is the radius. The upshot of this representation is you don't have to remember how to convert between rectangular and polar coordinates, or how to combine them. The algebraic structure of the expression just handles that for you, which can sometimes make polar coordinates a lot cleaner to manipulate. Wouldn't it be cool if we could do the same thing with spherical coordinates in 3D? Let's see if we can. As a reminder, the way spherical coordinates work is a vector in 3D space is described with three numbers. A radius ρ representing the vector's length, an angle theta representing the angle its projection onto the xy plane makes with the positive x-axis, like a longitude, and an angle phi representing the angle the vector makes with the positive z-axis, which is kind of like a reversed latitude, the angular distance from the North Pole. We can think of these three coordinates as specifying three different actions that, when performed one after the other, are capable of constructing any 3D vector. Start with k hat, the vector of length 1 pointing in the positive z direction. Then the spherical coordinates ρ, theta, phi can be thought of as instructions to take this vector and rotate it phi radians toward the positive x-axis, getting its co-latitude correct. Then rotate it theta radians around the z-axis, getting its longitude correct. And finally, scale the vector up by a factor of ρ. Each of these actions corresponds to a certain operation we can write down in terms of matrix algebra. Rotating k hat by phi towards the x-axis corresponds to applying the matrix given by the exponential expression e to the phi k hat tilde I hat. Similarly, the second rotation of theta about the z-axis is described by e to the theta I hat tilde j hat, since a rotation about the z-axis is the same as a rotation of the xy plane. And finally, scaling up by ρ is just a simple scalar multiplication by ρ, and so a complete algorithm for computing the 3D vector corresponding to a triplet of spherical coordinates is given by this tight little expression involving the product of two matrix exponentials and a scalar being applied to the unit vector k hat, where, remember, the actions are read from right to left. So the phi rotation happens first, followed by the theta rotation, and then the scale by ρ. The order is actually critical in this case, since swapping the theta and phi rotations will result in a totally different transformation. Specifically, the theta rotation will get completely ignored, since rotating k hat about the z-axis leaves it unchanged. At this point, you might be wondering if we can simplify this product of exponentials, and those of you with some foresight might be starting to get worried about something. Because one of the core algebraic properties of exponentials is that multiplying them together allows us to add their exponents. So it's tempting to simplify the product of these two exponentials into the single exponential e to the theta I hat tilde j hat plus phi times k hat tilde I hat. But something about this smells fishy. Because if we can add the exponents like that, what's to stop us from swapping the order of the sum and then applying the exponential combining rule in reverse to factor this single exponential back out into a product of two exponentials, but this time with the factors in reverse order? It seems we've managed to swap the order of the rotations, even though that's supposed to be impossible. What's going on here? The sad truth is that although the matrix exponential shares many of the algebraic properties of the regular real or complex exponential, this is one property it doesn't. You can't always combine a product of matrix exponentials into a single one by adding their exponents. This might seem like a pretty fatal blow to its worthiness of even being called an exponential function, since, as I said, this combining property is a core property of regular exponentials. But to its credit, the matrix exponential does the best it can. It turns out that whenever two matrices, A and B, happen to commute, that is, A times B equals B times A, then the exponential combining rule works as expected, e to the a times e to the b equals e to the a plus b. Now at this point, you'd be right to feel a little nervous trying to do any more algebra with matrix exponentials. If the fundamental combining rule only holds conditionally, what other traditional rules might be broken? So it makes sense before going on to briefly go over the algebraic properties matrix exponentials do have. The good news is we've pretty much seen the worst of it. Most of the other algebra rules you're used to for exponentials still hold true for the matrix exponential. I'll put up a decently wide selection of them on screen here in case you want a closer look, but you don't need to know all of this for what we're going to be doing. The main thing to keep in mind is the exponential combining rule only works on condition that the matrices in the exponents commute. Alright, with that out of the way, let's see what we can do with this new representation of spherical coordinates. One of the great uses of the exponential representation of polar coordinates back in 2D was in extracting derivative information like velocity and angular velocity, since the derivative of an exponential is so easy to take. So let's try something similar here. Let's say we have a moving point on the surface of a sphere, and we want to calculate its velocity vector at any moment in time, so both its speed and direction, given only two functions, theta of t and phi of t, that represent the point's spherical coordinates at time t. Here we'll take the radius to just be the constant 1. You can see how this might be tricky to think about. We have two interacting angular speeds to keep track of, and the way those angular speeds translate into linear speeds isn't totally straightforward, as it depends on your latitude, so to speak. A high theta speed means much more linear speed near the equator than it does near the poles. One way to do it, of course, is to plug in our theta and phi functions into the classic formula that converts spherical coordinates into rectangular coordinates, and then take a derivative from there. But you probably don't need me to tell you about the algebra nightmare that will ensue. And in the end, we might just get a gobbledygook formula that we have no idea how to intuitively interpret. But let's see what happens if we try using our new 3D Euler representation instead. Since we're taking the radius to be just 1, we can drop rho from our expression. Now let's take a derivative. Just like with regular real-valued functions, we can apply the product rule to get the derivative of the first times the second left alone, plus the first left alone times the derivative of the second. Note, however, that the products here have to be in this order. Remember, matrix multiplication doesn't necessarily commute. As for k hat, since it's just a constant vector, it just hangs out on the outside. From here, we need to take the derivative of these matrix exponential expressions. And once again, it behaves just like normal, including the chain rule. So both derivatives can be computed as the original exponential left alone times the derivative of their exponents, which are just the derivative of theta times I hat tilde j hat, and the derivative of phi times k hat tilde I hat. However, one cool thing to note about using the chain rule with a matrix exponential is that you can actually place the exponent derivative on whichever side you want of the exponential, and it doesn't change the result. In other words, a matrix exponential and the derivative of its exponent are guaranteed to commute with each other. For now, I don't have a very clear reason to prefer one side over the other, but I feel a vague aesthetic instinct to keep the chain rule detritus from mixing between the two matrix exponentials, so I'll move the derivative of theta and I hat tilde j hat to the left for now. Another thing we can do is note that the phi derivative, like the theta derivative, is just a scalar, so it's free to be multiplied anywhere in the product. So to further clean things up, I'll move the derivative of phi all the way to the left as well. And I'll also distribute the k hat so we can get rid of the giant parentheses. And now from here, perhaps we're ready to notice some interesting features. On the left, we have the derivative of theta, I hat tilde j hat, multiplying what is, in fact, the original expression we started with before taking a derivative. So we can replace it with r of theta and phi, the position vector of our sphere point. But now notice what this is saying. It's saying one component of our velocity vector can be computed by taking our original position vector and applying the tilt product, I hat tilde j hat, to it, scaled by the derivative of theta, the horizontal angular velocity. And remember that multiplying a vector by a tilt product means projecting that vector onto the plane spanned by the vectors being tilted, and then rotating 90 degrees in the direction from the first vector toward the second. So what this is telling us is one component of our velocity can be computed by projecting the position vector down onto the xy plane, rotating it so it points in the direction theta is changing, and finally scaling it by the speed theta is changing. So that accounts for the first component of our velocity, but what about the second component? Unfortunately, this one can't be factored into something involving the original position vector as easily, since the tilt product of k hat and I hat can't be moved all the way to the left of the two exponentials, because it won't necessarily commute with the theta exponential. Okay, let's move the tilt product back to where it started. What can we say about it right now? We have k hat tilt I hat multiplying k hat itself. Test your knowledge here and see if you can tell me what it has to equal. I'll wait a second. Remember, k hat tilt I hat means project onto the xz plane and rotate 90 degrees from z toward x. But k hat is already in the xz plane. In fact, it corresponds precisely to z itself. So rotating it 90 degrees toward x simply turns it into x, or I hat specifically. So we get what looks like the original position formula, except k hat has turned into I hat. How do we interpret that? Any ideas? Well, changing k hat to I hat here essentially means we've pre-rotated our position vector in the phi direction by 90 extra degrees. So replacing k hat with I hat is like sticking an additional 90-degree k hat to I hat rotation before the main phi exponential, which we can combine with the other k tilt I rotation to get a rotation of phi plus 90 degrees from k hat toward I hat. So one way to interpret what we have here is it's r of theta, comma, phi plus 90 degrees, all scaled by the derivative of phi, the angular velocity in the phi direction. So putting all this together, we've learned something interesting. The tangential velocity of a point moving around on a unit sphere can be decomposed into two components. One from projecting the position vector onto the xy plane and rotating it 90 degrees therein, scaled by its horizontal angular velocity, and the other from taking the position vector and rotating it 90 degrees southward and scaling it by its vertical angular velocity. If you take a step back, this kind of makes sense. As the point moves closer and closer to the north or south pole, the contribution of its horizontal angular speed to its linear speed should be less and less, which is perfectly accounted for by how we project the position vector onto the xy plane. Position vectors that are near vertical will have small xy projections. Meanwhile, the contribution of the vertical angular velocity should be the same regardless of its position on the sphere, so there's no additional projection factor needed for it. If that interpretation made sense to you, it might seem like the more obvious approach to take in solving this problem instead of doing all this matrix exponential nonsense. But still, isn't it cool how following this somewhat funky-looking algebra just naturally gives rise to this elegant interpretation? You can't say that so easily about the algebra nightmare from the spherical coordinate formulas. And that's why I think this matrix exponential approach has some real value. I'm not putting it out there as a replacement for any other approach to 3D rotation, but given its charm and elegance and the symmetry it bears to the classic Euler's formula that everyone agrees is super important, I think this approach is worth seeing, at least once in your life. Alright, now there are still a couple of other things I'd like to cover before wrapping this topic up, like how to use the formula if the two vectors in your tilt product aren't perpendicular or unit length, and also finding a way to rotate a vector by the angle between two other vectors without having to know what that angle is. But I think we've covered enough for one day, so I'll save those for one final follow-on video. But before I close, I'd like to give a quick shout out to all those supporting these videos on Patreon. Videos like this one that go deep into some pretty advanced topics don't always perform as well as other topics I could cover, and so your support on Patreon helps me justify the effort. It's thanks to patrons like these that I feel more free to make niche content like this. So if you find these kinds of videos valuable, consider supporting them by becoming a patron yourself, if you're able. You'll also get early access to new videos and a chance to critique them before they go live, as well as other goodies like behind the scenes or cut content. As always, link is in the description.